find angles that are not on the unit circle using the exact values. So let's look at this introductory question. Let's say we want to find two angles that are on the unit circle that sum to a value of 105. You could probably think of a couple examples. The easiest ones I think of are 60 and 45. 60 plus 45 is 105. Now, if I was to take the sine of those two angles and add them together, do you think it would give you the same answer as what the sine of 105 is? Well, let's check. Let's plug our calculator into degree mode and see. If I plug this into my calculator and I calculate what the sine of 45 plus the sine of 60 is, I get a value of approximately 1.57. But when I take the sine of 105 degrees, which is 45 plus 60, I get a different value of approximately 0.97. So clearly I can't just add the values that I have on the unit circle to find an angle that's not on the unit circle to find the exact values. How do we do these types of problems then? This is where our sum and difference identities come into play. This is coming from section 5.3, and of course your sum and difference identities that you have on your cheat sheet. Let's talk about where these sum and difference identities come from. So I'm going to go through an example here to kind of derive this formula that we have. You don't need to memorize this, you don't need to write this down, just follow along and see if it makes sense as we work through this. So I'm going to create two different angles, angle U and angle V. So angle U is my larger angle here, starts over here, opens up to this line here. So this is my terminal side of my angle. And of course this would be a point on the unit circle, cosine U, sine U, because of course our angle was U. Then we've got a smaller angle here, which is angle V, and of course this is the terminal side of the angle, and it ends in a point on the unit circle at cosine V, sine V. So what we're really focused on is not just these two individual angles, but the difference between these two angles. So if I was to say theta is defined as angle U on a larger angle minus angle V, we know what we're trying to find, this value of theta here. Let me take the same picture which we have drawn, but let's draw it so it's a little easier to think about. Let's take this angle and put it in standard position. So if I took that angle that I had theta and I draw it in standard position, this is much easier to work with, because then the starting side of my angle starts at a point at 1, 0 on the unit circle, and then my ending position is only at cosine theta, sine theta. Remember that theta was the difference between these two angles. So hopefully these coordinates make sense. So here's the picture before, here's the picture after. Again, theta is the same angle in both of these pictures. And so if that's true, it should make sense that the distance between A and B and the distance between C and D should be the same. Well, how do we figure that out? Let's look at the distance formula. The distance formula is defined as so. So if I plug in the values that I have, I just need to know the x and y coordinates of my two endpoints to find what the distance is. So for A to B, this would be my formula. And from C to D, this would be my formula. And because we know that these two angles are the same, their distances should be equivalent. So there's the start. We've basically taken our distance formula, something we're familiar with, looked at one in standard position and one in out of standard position. So let's do some algebra. Again, you don't have to do this, just follow along and see if it makes sense. Pause it if you need to stop and take a closer look at it. But here's the statement I just had before. The two distances have to be equal. Let's get rid of these squares. They're kind of in the way. So square both sides. That takes care of that. That's really nice. All right, now let's go ahead and simplify a little further. Let's go ahead and FOIL this out or multiply this out. This is going to be long, but that's because we've got two quantities squared on both sides of my equation. So we know our cosine V minus cosine U quantity squared is going to give us this quantity right here. Our sine V minus sine U quantity squared is going to give me this quantity here. Our cosine minus 1 squared is going to give me this quantity here. And of course, sine squared, or sine minus 0 quantity squared is going to give me sine squared. So that's pretty straightforward. All right, let's rearrange this a little bit. If we regroup these terms a little bit so they're easier to work with, you should see something, particularly those that have the angles U and V. If I group together these angles that have V and U, you should notice something we've seen before. Cosine squared plus sine squared. That's an identity. We know that's going to be 1. It's true for all three of these. So let's go ahead and plug that in. Let's replace using the identity, and we see all these values become 1. Way easier to work with. Well, now let's try and simplify a little further, because we still have some values we can simplify. So if I combine my terms, here's what I get. Basically my 1 plus 1 gives me 2. My 1 plus 1 over here gives me 2. Wow, they got a lot of 2's in here. Let's divide everything by 2 and see if it can simplify. So I divide everything by 2. I can see I can cancel out the 1 on both sides. Simplify that. Let's also notice that they all have negative 1 in front of there. So let's divide that out, get rid of that. And here's what I end up with. So we have a formula here that says if I want to find the cosine of the angle theta, I just need to know the cosine and the sine of both those individual angles, U and V. Remember that our angle theta was the difference between U and V. So this is one of our formulas for our sum and difference identities. This is probably what you're going to see something similar on your cheat sheet. Of course, instead of U and V, which is what your book uses, they say alpha and beta. So again, two different angles, noting that that's the difference between the two. So your sum and difference formulas, one of them we just looked at was here. So the cosine of U minus V can be equal to the cosine of U times the cosine of V plus the sine of U times the sine of V. Notice something here. There's a switch in signs. We have the difference between the two, but we have a plus symbol here. That's important to note as we work through this. Here's an example using this. Let's say we wanted to find the cosine of 15 degrees, not an angle on the unit circle. But there are two angles on the unit circle, 45 and 30, that if I take the difference of them gives me 15. If I plug in 45 every time I see U in my equation, and 30 every time I see V in my equation, we end up with cosine of 45 degrees times cosine of 30 plus sine of 45 times sine of 30. And then using our unit circle, you can see where these values hopefully come from, because sine and cosine of 45 is square root of 2 over 2, or 1 over 2. And cosine of 30 is square root of 3 over 2. And sine of 30 is 1/2. So when I multiply, I notice, wow, okay, square root of 3 times square root of 2, square root of 6. 2 times 2, 4, and so forth. We have a common denominator. Let's go ahead and write them together. This would be the answer I would be looking for if I said find the exact value of the cosine of 15 degrees. Now, this is not the only way that I could do this. I just need two angles that are on the unit circle, so when I subtract, I get 15. So 60 and 45 would work too. You'll still end up with the same answer of the square root of 6 plus the square root of 2 all over 4. Don't believe me? Let's use our calculator to check. If I was to plug in the cosine of 15 degrees on my calculator in degree mode and plug in this quantity that we got, you should see the answers are the same. And indeed, they are. You also notice under sum and difference formula there was one for the cosine of U plus V. Again, notice the switch in signs. When we had the sum of the two angles, we've got a subtraction sign in the middle here. And again, just showing you an example, again, taking our answer of 105, breaking it into 45 plus 60, plugging our numbers in from our unit circle, you can see the value we're going to get is similar to our answer, but not the same. A lot of our answers are going to end up something with square root of 2 and square root of 6, plus or minus somewhere in there, over 4. Almost all the answers are going to be very similar to that, just because there's a number of values you could get with what you've got on the unit circle. Again, verifying your calculator, you can see that gives you the same answer. So what's on your formula sheet? Well, we don't write them individually as two separate sum and difference formulas. We write them together. And no, that's not a typo here. Whoops. Notice that we've got the plus or minus here, and then a minus plus. Why do you think that is? Well, if we think about the formulas we just talked about, when we were trying to find the sum of the two angles, we separated them with subtraction. When we had the difference, we separated them by addition. So it's not a typo. These really are meant to be. If it's plus here, then it's minus here. If it's minus here, it's plus here. So take a look at your formula sheet and see that that's where that is coming from. Now, how would I use this to find a problem like this? Find the exact value of this quantity below. Well, 78 degrees and 18 degrees are not angles on the unit circle, so clearly we need to use one of our formulas. I notice a pattern here. I've got cosine, cosine, sine, sine, and if I go backwards in my formula, I would see that that's basically like saying the cosine of the quantity, 78 degrees, minus 18 degrees. Again, because the sign here is plus, this is going to be minus. Well, 78 minus 18 is 60, and the cosine of 60 we can do on our calculator or on our unit circle and find that it's going to be 1/2. So know how to use this sum and difference formula both ways. From something that would ask you to find a cosine or a sine of an angle that's not on the unit circle, or to simplify and combine it to get something that was on the unit circle. Remember, you have sum and difference formulas not just for cosine, but we also have them for sine. Here's an example of what that is. Notice that for the sign, the SIGN sign is the same between the two. So this is plus, this is plus. So again, plugging them in, you're going to notice a lot of similarities in the types of answers you get. And in the same respect, we've got sine of the quantity U minus V. Again, notice the minus here. And again, notice the order. It's not the same. It's sine, cosine, and cosine, sine. So we use these formulas a lot to find angles that are multiples of 15 degrees. These are angles that are not on the unit circle, but can obviously be manipulated using angles that we find on the unit circle. So what's on your formula sheet for sine? Notice again, you see the plus minus, but you see the plus minus here. And again, that's because the same sign on the top is the same sign you're going to have in the other part. So let's actually use this function we just talked about to verify one of our co-function identities that we had on our sheet. If I wanted to verify, besides saying it's an identity, that the sign of the quantity pi over 2 minus x equals cosine x, we can use one of our formulas. That is, the difference formulas for sine. We can see that we can separate this as kind of our two angles. This is my alpha, my beta, or u and v. So this would break into sine of pi over 2 times cosine of x minus cosine of pi over 2 sine of x. Well, we can't do anything with the x terms, but we do know what the sine of pi over 2 is and the cosine of pi over 2 is. So if I plug that in, we see we get 1 times cosine x, which is cosine x, minus 0 times sine x, which is just 0, so our answer is going to be cosine, which obviously was our identity. So there's a little song to help you remember this. I will give you the sum and difference formulas, but some people kind of like to remember them because they use them often. Again, it just depends on the order. Remember that for sine, you've got sine, cosine, and then cosine, sine. And then cosine, you've got the two cosines, the switching of the sine and the sine. And it's nothing fancy. It doesn't even go with a familiar tune. It's just sine, cosine, cosine, sine, cosine, cosine, sine, sine. It may help you remember that, it may not. You've got the formula given way, but I always get stuck in my brain, so I kind of remember the order that they go in. And I just remember that the sine, the S-I-G-N, sign of the sine is the same and the cosine's the opposite. Now, obviously, you have ones for tangent, and this one is not one I'm going to ask you to memorize. This is obviously one that's going to be given to you. Tangent is nice. However, remember that there are some values where tangent is undefined. So this is somewhat helpful, but there is another way you can do this. Again, notice that the plus or minus is the same on the top, but it's reversed on the bottom. When this doesn't work out because you have a tangent that's undefined, remember that you can always define tangent as sine over cosine. And since you already know your sum and difference formulas for sine and cosine, that's essentially all you're doing is taking the sine over the cosine. So know that both of these formulas are fine. This is the first one, the one that's on your formula sheet, but know that this one also could be used. And you'll find on some of your assignments, this one is actually easier to work with.